Hello everyone, welcome to day 14 of our machine learning internship. And till now we have seen all the pre-processing steps, basics, etc. So our ultimate step is going to be learning about the machine learning algorithms. So we'll be taking 3 sessions entirely to discuss about what is each algorithm, their names, what is their roles and responsibility, how they will work, what's the max behind it, what is actually happening when you actually use it from your scikit-learn library. So that's what we will be discussing in the next few days, which will be day 14, 15 and 16. And in day 17, we will be having hyperparameter optimization and how to evaluate your algorithms in day 17. After that, from day 18, we have projects and then moving towards higher concepts like NLP, deep learning and time series forecasting, etc. So starting our day 14, so we'll be seeing some introduction about how or what's the procedure for you to choose a machine learning algorithm. In that pathway, we'll be starting with important algorithm groups which are called as linear models. So this linear models, which consist of a lot of algorithms inside, which is prominently usable algorithms like linear regression, logistic regression, ridge, lasso, etc. So you'll be seeing the important 4 concepts in this session, which comprises the linear models. So that will be our task in today's class. So without any delay, we'll get started. So once again, I just want you guys to refresh what all things we have covered and where we are now. Starting with the steps in machine learning: data collection, over pre-processing, train test split, and feature selection, about it. Fine. Coming into model selection, okay, you can select any model from scikit-learn. You need to have any idea, just a basic idea about how to choose algorithm, and then you can just go with that. You can train it with your training data and then make predictions with your testing data. You can evaluate and improve it, and there are way to make a predictive model also. So if you give one row detail, like for example your blood pressure details, etc., so it will give you whether you are susceptible to diabetes or not. So like that, you can create a predictive system too. Fine. So now the important deciding factor here is the model or algorithm, which is nothing but a statistical tool. So how to select? There are lot of options available, not only from scikit-learn library. You have other options too. So how will you select your algorithm? Starting with that, let us see how to choose the right machine learning algorithm. So the factors you need to be considered is the nature of the problem, nature of the algorithm, and performance comparisons. Okay, so you need to understand your data, what you are going to solve there. That will comes under the nature of the problem, and also you need to learn about the nature of algorithm so that you can understand, if I use this algorithm, what is happening there. If I use this set of algorithm, what will happen in it. And finally, you can also go with performance comparison, and you can choose some other algorithms later and do a trial and error method to find your best algorithm for your particular data set you are having. Starting with the nature of problem. So talking about the nature of problem, we need to understand the types of machine learning. So we have supervised learning, unsupervised learning, and reinforcement learning. So mostly we'll be having different algorithms for supervised, different set of algorithms for unsupervised learning, and different algorithms for reinforcement learning. Reinforcement learning is actually a different field, which is like, it's actually an entire differently in-depth field. So you need to have the basic understanding of supervised learning, unsupervised learning, then study a lot about deep learning. Then only you can take an introduction to reinforcement learning and proceed in that pathway. So as basic step, we need to learn about supervised and unsupervised. When you talk about supervised learning, again it has 2 types. One is classification, another one is regression. Talking about classification, we have a lot of classification algorithms, and some of them also play dual role, like that algorithm has application for both classification as well as regression. So you'll be using 2 different modules for it, and in the same name. For example, I can show you like decision trees or support vector machine or random forest. So this will be available both. You can have options for a classifier as well as a regressor, as well as you have some unique algorithms. Like for classification, we have logistic regression. For regression, we have linear regression, etc. We'll be seeing about it. So that's it about our supervised learning. So you have a lot of new names here. So we will be learning about them. And coming to unsupervised learning, we have clustering algorithms. So when you talk about unsupervised learning, the data won't be having any labels. So here your task is to find who all things are grouped together and who are all unique, who are all different. You need to find them. Then you can separate and identify how these all the categories it can be separatable, and that is what exactly we'll be performing in the clustering. Talking about clustering, we have different algorithms like k-means clustering, mean shift clustering, db-scan clustering, etc. So prominently we'll be using some algorithm which is k-means clustering, an important application. So clustering will try to cluster your data points and find cluster groups there. That is what will happen in our unsupervised learning. And in reinforcement learning, the target is to make decisions. So we'll be having an environment, and for every action there will be a reward. With that, the algorithm needs to improve its reward, so it will work on it, so that every time it fails it tries to improve it. So if it's correct, we will be giving it a reward which is high. So every time it runs, every time it fails, over the time it will learn to pass every test you are giving, so it will do it perfectly. That's how our reinforcement learning works. Complete the basics and then you can go and start with reinforcement learning. Focusing on this, you need to understand the nature of the problem. So once again, based on you are having a supervised learning or unsupervised learning or reinforcement learning, you need to decide your objective based on your data set. So in that data set also, if you have labels, then it will comes under either classification or regression. Then you need to decide if your data set is regression data, like a selling price you are going to predict, that is your target, then it's actually a regression. If you are going to predict either yes or no, 0 or 1, hot or cold, that is actually a classification. Not only these two, you can have multi-class also. Either A, B or C, you are going to predict in these three. Mild, severe, or like that. If you have three classes, then you can predict in that too. So now that is what the first step is. So now you need to know that some of the nature of the algorithms and their names. Like that, we can have different set of algorithms here, right? So for if it's a classification problem, you can select any of these, or regression, you can select any of these. Like that, with the nature of the problem, you can decide or categorize your algorithms. Now if I have a classification problem, I have a set of algorithms here. So if I want to utilize it, then I need to know about them. You can just import it and use it, but what's actually the use of it? You need to learn more about it, what is happening behind as a machine learning scientist. We'll start with our linear models. So in linear model, we have algorithms like linear regression, logistic regression, lasso and ridge. So that is what we'll be seeing in today's session. And let us start with linear regression. So analyze the term linear regression. So I'll explain what is linear regression. So linear regression is a popular and widely used supervised learning algorithm in machine learning, and it's actually a statistical term and a statistical tool which assumes a linear relationship between variables, meaning the relationship can be represented by a straight line or a scatter plot on a scatter plot. And linear regression can be used for prediction of dependent variable with one or more independent variables. So I'll just clarify before going into the next slide. I'll clarify once again, it's one of the popular tool for supervised learning. It's actually for regression. Okay, it's having regression in its name, and it is used for regression. Not only like that, for example, we have another algorithm which is next we are going to use or see about logistic regression. But actually logistic regression is actually for classification. There's actually some difference between them. I'll tell you later. But linear regression is for regression problem. It is a statistical method which assumes a linear relationship between the variables, meaning the relationship can be represented by a straight line. Remember the term straight line on a scatter plot. And it can be used for predictions of dependent variable with one or more independent variable. So in this context, what is dependent variable is nothing but your target column. We are talking about regression, right? I just want to quote an example. Once again, we'll stick with our selling price of our car. So that has lot of numerical values, or a temperature which you are going to predict, which is a continuous variable. It is a regression problem. So that is your dependent variable. So what is mean by independent variable? What is mean by independent variable there? Independent variable is nothing but your features. For example, what all features you have? Car year, car name, and what all details else we have. What is the fuel type? How many owners it had, okay, whether it's a second hand car or it's more than that, okay. So like that, you can have one feature or multiple feature. That's what they have defined as. Linear regression can be used for prediction of your dependent target with one or more independent features. So features are independent, only your target is going to be dependent to this independent variable. What is one or more? I can tell you, for example, imagine our car data set. You are going to predict the selling price. So you have to predict the used car price now. So what does that means is, consider only one column now, one feature, one independent feature, which is going to be the year it has been bought. Okay, the first owner, the first time it has been registered, the year. Or you can consider it as a age. So if the age is less, which means it is a newly bought car, only few years or few months that it has been used. If it is in good condition with that, okay, then its price will be really high. Imagine a car which is already used for 15 years or 20 years, it's very old car. Then what will happen? Obviously, your dependent variable, which is target or selling price, is going to be low, right? So that's how we will be using the relationship between independent variable and dependent variable to find, okay, by plotting it in a straight line on a scatter plot. I'll show you. So we will be having our independent variable. It can be one column, one feature or multiple features, and this y is going to be our prediction value, which is target. Okay. So what we are doing is we are plotting it in a scatter plot and try to fit it in a straight line. Okay. For example, if you are having consider the value of x, we can see it with this example, which is actually good. See here you are having only one feature, which is rainfall, and your target here is to find how many umbrellas sold, and you are plotting it in your data set. When you give it to your linear regression, it is trying to fit in a scatter plot. See here, for example, the rainfall value is 80. Okay, when the rainfall in millimeter is 80, the umbrella sold is around 15. And then like that, when you have rainfall is around 100 millimeter, the umbrella sold is around 30. So like that, we can see a trend here, right? Can you see it? When the rainfall increases, the umbrella sold is also going to be increased here. So now you are fitting it in a straight line. So now if I have a new point, for example, now since I am having this straight line, what I can do is, if I want to predict, listen here, I am going to predict if, okay, tomorrow or today the rainfall value, or this month the rainfall is around 150 millimeter. So what will be the umbrella sold? The prediction can be, you can use this line. So in 150, what will be your y value? Nearly 50. So you can tell approximately around 45 to 50 umbrellas can be sold in this period based on your data. That is what called as prediction when you go with this context of linear regression. This is rainfall. You can have multiple features like rainfall or something else, etc. features we will be having, right? A lot of features. So like that, okay. Or imagine your x-axis as your number of age of your car, and y is the selling price. So when the age of your car increases, the selling price will decrease. So it will be in the reverse trend. This is increasing trend. So when this increases, this will decrease at that time. So when the age is less, you will be having higher value here. So you will be having a straight line in this manner, in the reverse manner. Now what you can use is, if you want to find a value, you can plot it in this line and get the value of your y. That's how this linear regression uses statistics and maths to find or give you prediction. So we'll understand furthermore about the straight line. Now we'll be moving towards mathematical part. I hope this example makes you clear how we are actually training our data and making prediction. Training means just the statistics is happening in linear regression. Data points will be plotted and the line will be fitted. Now with this line, If you give a value of x, then with that, in that intercept, it can give you the y intercept, that will be the value of y. So for example, if you want to predict what if the rain value is around 80 millimeter only, then you can go and predict that. So if you have a new point which is less than this, you can elongate this data point and try to fit where your umbrella hold is. So moving with the next one, we'll discuss about the equation of straight line. So when you talk about straight line, you would have learned about this term, which is y equal to mx plus c. Okay, so y, your new y value is going to be mx plus c. What is m here? M is the gradient. So talking about gradient means the difference in y divided by difference in x. So if you have a straight line, see here, if you are having 2 points, when you have a slope, the difference in x is going to be this value, x2 minus x1, and difference in y will be y2 minus y1. When you take these values and divide, you will be getting the value of m. And c is the intercept. So what is c is, you are having this line, right? So when you pass this line, if you elongate this line, in which point it is crossing your x value, in which point it is crossing your y axis, this point, if you elongate towards here, when it crosses towards your y, what is the point here? It will be around 12 or 13, right? That is your y intercept. See here, the line, when your slope line, when it touches this y axis, that is actually c value. So that's what our intercept and gradient is. From this equation, you know x value. So if you have a x value, if you want y value, you can plot it like this, or you can use this formula, which is y equal to mx plus c. Calculate the value of x, calculate the value of c. You have value of x now. If you pass it here, you will be getting your prediction value y. That is what happening in our algorithm, linear regression. Consider once again this used car data set. Now it will make sense. We are having the present price, and here we are using single feature. You can have multiple features. So if you pass multiple features, then based on that, a line will be fitted, the data will be plotted, and with the line it will give you answers. So that's what called as a simple versus multiple linear regression. When you go with simple linear regression, it is a regression model that estimates the relationship between one independent variable and one dependent variable. It's actually 1 versus 1 using a straight line like we had here. Or if you have multiple features, then it finds the relationship between 2 or more independent variables with one dependent variable, which is your target. And talking about simple linear regression, this is what that age versus price. When the age of the car increases, the price is obviously going to drop, and we can have a straight line like this. With that, we can use the straight line to get answers. That's actually really good. But you need to understand furthermore about this line you are having. So you should get this doubt of, okay, I'm having data points, but how is that line is passed there? So you can ask me, see here, these both are same data points. I have a blue line, I have a red line. Consider only one line now, consider blue line. It is actually passing through most of the data points in the center, fine. Now consider red line. With the red color line, I can see once again it seems like it is passing through most of the data points. But if you go with blue line, if you want to make a prediction, then the value will be different. Okay, it may be same here, but in this point, what will happen? Your blue will give you a result. But if you go with the red line, it will give you a result, different result. Now, how this linear regression works and how a best fitting line is obtained. Okay, what is the best fitted line? Like this, you can draw multiple lines here, and each line is going to give you a different prediction. This is actually chaos. How this uses and finds the best line. So the whole idea of linear regression is to find the best fit line which has very low error. So based on the error, we will be predicting it, that can accurately predict the value of the dependent variable based on the values of independent variable. So your aim is to reduce the error, or reduce how much low you can obtain, that much low error you need to get. So which line, if blue line is getting low error, then it's actually good. If red line is having the low error, then that is the best fit line which will be selected. So how will you calculate that error? We'll see now. So the line of best fit, it is determined by minimizing the difference between the actual and predicted value of your dependent variable. See here, I'm having the idea of this line is to pass through all the data points. If you plot a line, it should pass through all the data points, but it is not possible because in a practical scenario, can you draw a straight line which pass through every point? It will be zigzag line. You cannot have a straight line. So your idea is to find a best fit line which has low error, which means that, see here, you are having a line like this. See this image. So this is your original y. Okay, for example, this is your original point here in this place, in this space, but your line is going here, which means that for this point the value given by the line is this place. So it is trying to fit a center place where it can cover all the points. So the error will be calculated as what is your original value and the predicted value. See here, the residual will be for every point. This will be calculated, your given value and the original value, given value in your line. So like that, if you calculate for all the points, for example, you are calculating for your red color line, you are calculating for your blue color line. Finally, which line is having the lesser value, that will be given as the best fit. See here, your green color is your actual response, but this orange square is going to be the given response based on the line. Okay, so for these points it is fitting these places, but it will calculate it. The value will be calculated, this distance will be calculated, and which line is having very less that error value, the sum, if you sum all these errors, then whose value is very less, that will be the best fit line. Imagine a situation, okay, consider here your point is exactly fitting, all your points are exactly fitting on a straight line. You are having a point, you are having a straight line, and not like this, you are having everything going exactly through this straight line. Then what will happen? If line passes exactly through all the points, then there will be difference. The difference will be 0. Totally the value error will be 0. So your task is to minimize the error near to 0. But will it be possible here? In a practical scenario, you cannot have a line which passes through every data point. If it passes, the error will be 0. Because here you don't have any difference, right? If it is here exactly, all the points is here in the straight line, the value will be 0, error will be 0. But it's not actually possible in a real-time scenario. So your task is to reduce that, however closer you can get. If you have it, that will be your best fitted line, and that will be actually done by your algorithm with some simple mathematics. So before going into that max, we need to also learn the formulas. Don't get confused, this is just y equal to mx plus c. This is y value, this is c value, which is the intercept, which is b0, and this is mx. Okay, x is x1 and m is given as b1, and they are multiplying. So that's what y equal to mx plus c. If you consider multiple linear regression, what is multiple? So not only one feature, you are having more independent features, then your value, the intercept will be 1. Only one intercept will be there. Why? Because we are fitting one line and that will pass through the y only once. This will be 1, c will be 1, but you can have, since you are having multiple features, the formula will be like this: b1 multiplied by x1, then b2 into x2, then so on. How much feature you have, that much will be taken into account for your prediction. So your predicted value will be based on the formula, it will be given the result. Okay, about the independent variables, x1, x2 will be the independent variables. So if you have 10 columns, you will be having till x10. Then b0 will be the intercept, which is c. b1, b2, b3 are coefficients, and n will be the number of observation finally. So if you have like how many features you are having, that will be taken into account in this year. So the error is once again the y original value and the predicted value. So your task is to go with minimum error. So to achieve this minimum error, there is actually a method which is followed, which is called as ordinary least squares, which is OLS method. So the OLS method is used to estimate beta 0 and beta 1. The OLS method seeks to minimize the sum of squared residuals. So we need to get the value. If you know the value of beta 0 and beta 1, then you can actually, you will be having your x, you will be getting your answer, which is y, the prediction. But how to find? Okay, see here, beta 0 and beta 1 is nothing but the best fit or the fit of your line. So you can obtain it from your line. So if the line is a best fit, what is the value of beta 0 and what is the value of beta 1, or what is the value of m and what is the value of c in this formula? According to this formula, what is the value of m and what is the value of c if the line for the line which is best fit. Okay, if blue or red, whose value from beta 0 and beta 1 is best, that is found using OLS method, which is ordinary least square method. So it is a non-iterative method because it is just going to use max to find the answers of beta 0 and beta 1, which has very low error value. So you can actually get it from here and then use it in your data. So this is what the formula inside of it, you can actually do it. So if you are having your x column and y column, with that you can take your x hat and y hat and you can get from this formula. To find beta 0, you need to have your y hat minus b1 into x hat. So what if, or how will you find your b1? That you can find with summation of x minus x bar multiplied by y minus y bar divided by summation of x minus x bar the whole square. So with this formula, x bar is actually the sum of that entire x and x is that individual value like that y. So you can use this formula to get a value of b1. If you apply this beta 1 here, then you can get your beta 0, which is actually a best fit. With these two values, you can actually make prediction. And OLS uses calculus to find the values of the parameter that minimizes the sum of squared errors between the predicted value and the actual value. And this is done by taking partial derivatives of cost function with respect to parameters and setting them equal to 0. And the solution to these equations are the values of the parameter that minimizes the cost function. So the OLS matrix form, there is actually a matrix format also available for this ordinary least square. With that you can actually do this all the calculations using matrix format and get the result and verify with our linear regression, which we are going to do. So this can be helpful for understanding the OLS model and for performing calculations within the model. So this is the formula, note it down. So for finding beta hat, you need to go with, so this beta cap is nothing but beta 0 and beta 1 value, both of these values. So to find that, you need to have your x and y value. With that, you need to take a transpose of your x. In matrix, if you want to transpose, see here it is in this format, right? If you take a transpose, it will be in like the row wise, y, then y2, y3, etc. I'll show you. And you need to do a matrix dot product multiplication here, and that value should be taken an inverse. And with that, you need to make a dot product of your transpose once again. And with that, if you make a dot product of your y, you will be getting your beta 0 and beta 1 value. So that is your this beta cap value. So we will be doing hands-on. Before going into that, we can also simply use, once again, if you want to perform or use this linear regression, you can use it from sklearn.linear_model, import linear regression, and you will need to create an object for it, and then you can fit and transform it later. So I'll be doing, what I'm going to do is, before going into the next one, I'll be creating the model and I'll be making the prediction, and also I'm going to use this formula and attain the same result from scratch using matrix OLS method. We'll try to do both and verify whether both are giving the same answer or not now. So I'll focus and shift here and load a data set. I'll import pandas as PD, data equal to teams.csv. Fine, data.hit, it is actually a regression problem, and the task for us is to find the medals, which has been how many medals. Okay, so you can go with data of medals dot value underscore counts. Let us find whether it's a classification or regression. It seems like it's a regression problem. There are a lot of individual values inside. Fine, and these are some of the features you are having. The team, the year, athletes, how many people, events have they participated, their age, their height, weight, and how many previous medal they got, and what is the medal they have given or they obtained. You will be given a target which is medals, and these are all the features. So in X, for now, for example, I'll select only few columns, which is going to be the athletes count and the previous medals. And in Y, I need to take the target, which is going to be my medals. So for the matrix calculation, I need to have empty place, or I need to have 1 in all the place. So I'll create a new column in X, which is going to be intercept, which will be having 1 in all the place. This is for our matrix calculation. So that will make sense. See here. So now if I show you the X value, it is like this, right? So you can see it is 2014 rows and 3 columns. So now what I'm going to do is, for that formula, now I have X and Y, but I need X transpose value. So I'll create a new variable, X underscore T will be X dot T. So if you go with X dot T, it will give you a transpose value. So now if you go and use and check this variable, which is X underscore transpose. So now you can see when I take the transpose, this has been reversed and we have now 3 rows and 2014 columns. And what we are going to do is, we'll be having it, and we actually need to do this task, which is dot product multiplication here, and we also need to take inverse. For that I'll use NumPy. So NumPy has all the tools we need, linear algebra tools. So I'll use that. So one of that tool is np dot linear algebra. In that I need to take the inverse, and what I'm going to do is, see this formula, I need to take inverse of the dot product between X transpose and X. Now I have X and X transpose, so I'll go with X transpose. So to achieve matrix dot product, you need to use this at operator, at the rate you can give, and I need to make it with X. Okay, so once I have it, what I should do next, I need to have a dot product with that, with this entire thing, with X transpose and then with Y. So I'll repeat the same here, at X transport at Y. So if I run this, I'll be getting a result which is like this. So if you want to know what is this, I'll tell you. So I'll create a variable. For example, we'll go with output O equal to this one. So I'll set a index value, which is going to be, which is nothing but your X dot columns. So I'm setting index for our O. Yeah, what is X dot columns? Just first is athletes, next is previous medals, and third one is intercept value. Okay, so yeah, 1 minute. Now if I go with O, I can find the 3 values which I obtained. One is athletics, and another one is previous medals, and another one is intercept. Tell me guys, what is intercept actually? Intercept is the point which is the C value, right, where it passes your Y axis. Then what all these two, if you understand, then these are your M value for each of your feature. For athletes, this is the M value. For previous medals, this is your M value. If you have another column, if you just take the index, okay, last one will be intercept. If you have another column, then once again you will be having another column and its particular value. Okay, so now if I want to make prediction, what I can do is I have my, see here guys, I have my Y intercept value, which is C. I have my M values, which is M1 and M2 for 2 different features. Then you know the formula Y equal to Mx plus C, right? Here Y equal to C plus, you are having 2 features, so M1 x1 plus M2 x2, like that. So what you need to do is, you can use these values to actually make prediction. So I'll create predictions equal to X. You are having your X value. Okay, I'll make predictions for our X value, our X data, which is going to be just a features alone, right? So X at our O. So I need to do a dot product here with our these 3 values. Then the output will be like this. This is what your prediction is. Okay, so this is your prediction for all the values, which means your X value. If you have X train and Y train, if you have your X train here, if you make a dot product of it with this O now, so your prediction is going to be this one. Okay, so for that 2014 rows, 1 column output medals has been predicted and given in the output. So if we need to cross check, okay, this is what happening behind your linear regression. Usually we don't go and do all this with dot product. This is for just representation. So practical scenario I'll be taking from sklearn dot linear underscore model. You can import linear regression, and the model I'll create a variable which is linear regression, and my task is to first fit instead. So in a real-time scenario, we'll be going with our x train, y train value, which is nothing but x and y, right? So I'm not going to test it now, so I'll go with entire x and y here. Okay, so before fitting it with x, in x I'm having the intercept which is not required now, so I'll have it in my capital X. So these two are the features going to be. So I'll go with our capital X comma y value, which is the target. So it will learn now, which is nothing but it is fitting the straight line like what we did. If you want to cross check, what I'll do is first I'll go with model.predict. Once again, if you have new data, you can go and predict. But here what we made prediction is your x value, right? So I'll go and make your prediction for my x value only. So what I'm getting is the first one value is minus 1.392, and I can get minus 1.392 here. So the last value is 0.2425, 0.242587. Then what has happened? Your linear regression algorithm is giving the answer which is same as our answer, because we have just done the max behind it hands-on from the scratch. Okay, you can verify. You can create another data frame near to it and verify whether both are same. It will be same. Okay, so if you want to have some more verifications, once you fitted your model, you can call it to model dot. You can go and get some parameters, which is, see here, we can go and get some of the concepts like intercept. So it is giving me the intercept value here. Intercept is C value, which is the place where the line passes your y-axis, which is minus 1.9618. What is my intercept from my task, which is minus 1.9618. I have also predicted the same. Okay, so if you want to get this coefficient, okay, these values for athletes or previous medals, what you can do is, once again, you can ask your model to go and call for coefficient underscore. Once you fitted it, you will be getting values. This is 0.711 and 0.7341. 0.711 and 0.7341, the same values. So this is what happening behind our linear regression, and simply we can use by importing it and doing like this. This is just a mathematical representation of the matrix format. So we'll move towards our next algorithm, or before continuing with the next one, there are some regularization options available in linear regression. So I'll tell you what is regularization and what is the need for it. So regularization is a technique used to prevent overfitting in machine learning model. What is overfitting? Overfitting occurs when a model learns the noise in the data too well, and as a result it does not generalize well to a new data. So for example, overfitting is like overlearning. So imagine here the straight line we are having, right? For example, you are having lot of points here, so for reducing the error, so this task for this algorithm or linear regression is to find the best fit which has less error for this particular data. Fine, that's good. So now if you have more points here, to reduce the error, your line will be stretched towards here. So now for this data, your error is good, fine. But what is our ultimate aim? For new data, you need to make prediction, right? But what if you are having a point here, okay, so your line is now more tilted towards this side. For your new data, if you are going to make prediction, if your new data is here, then it will perform well. But if your new data is here, what will happen is your line is more tilted, but the prediction will be get altered because your model is overfitted the points. That is actually an issue which you need to sort down. That is what called as overfitting. And to avoid this overfitting, it happens only when your algorithm learns the noise, which means it is trying to reduce the error, and it may go either side in some cases like this in overfitting. To reduce the overfitting, we can use this regularization technique by adding a penalty to the model's complexity. So we will be adding a penalty term to the error calculation. So this penalty penalizes the model for having large coefficients, which helps to keep the model's prediction from being too extreme. So it will now adjust your error values so that it cannot be too biased or overfitting or too extreme on one side. So talking about regularization in linear regression, we have two main types. One is lasso regression, another one is ridge regression. So lasso regression uses L1 regularization and ridge uses L2 regularization. Ridge regression, talking about that, it works by adding a penalty term to the cost function or error calculation of a linear regression model called as the regularization term. And this regularization term prevents the model from overfitting by penalizing the large coefficients. So this is what happened. So in the cost function, what will happen is it is going to add a hyperparameter to your slope value. So this lambda what it will do is it will adjust these values so that the error calculation is going to be altered based on this hyperparameter lambda value. So if I want to tell you an example, see here. So the main idea behind ridge regression is to find a new line that doesn't fit the training data as well, which means that we introduce a small amount of bias into how the new line is fit into the data. See here, you are having your training data, which is this red color line. You can draw a red line like this, which is perfectly passing through the points. But imagine a situation like this here. Your prediction or the testing data is going to be like this. So if you have it in red color line, it is actually not going to be a good prediction, right? To avoid that, now we are adding a bias value, which is now altering your error value so that this line will be adjusted like this. The new line is this blue color line. So now if you have a new point, you can see they can also be equally contributed from here. That is what the idea of ridge regression. And that lambda here, right? So this hyperparameter is the factor that controls the amount of regularization that is applied to the model, and a higher value of lambda leads to strong regularization, resulting in more pronounced shrinkage of the coefficient value. So conversely, a lower value reduces the amount of regularization, allowing the model to fit the data more closely. And to perform this, you can use a ridge from your linear underscore model. So I'll show you how to import it from sklearn.linear underscore model, import ridge. So this can be used, you can create models and use it, the ridge regression. Talking about the next regularization, which is lasso, and this penalizes the sum of the absolute values of the coefficient. Based on the coefficient values, their absolute value is taken. This means that the coefficient are encouraged to be small, and some of them may even be set to 0, and this helps to prevent overfitting. So in that slope, you are actually performing this task by taking the absolute value of the slope values along with this lambda. So here, if you saw the formula, we don't have that value, right? So we don't take here, but when you see here on lasso, the absolute values are taken and that is added as the cost, and that will also help you to avoid overfitting. And you can use from sklearn.linear model, import lasso, you can create an object for it and use it. Along with ridge, you can also use lasso. So these uses linear regression only, but along with that you are having regularization added to it. So moving towards the next algorithm, we have completed linear regression, lasso and ridge. We will finally see the logistic regression from our linear models. Talking about logistic regression, it is much similar to linear regression except how they are used. See here, even though the name is logistic regression, the algorithm is used for classification problem. So logistic regression is similar to how it is used in linear regression, except, okay, so linear regression is used for solving regression problem, whereas logistic regression is used for solving classification kind of problems. In logistic regression, in linear we have fitted a straight line, right? Here in logistic regression, instead of fitting a regression line, we fit a S-shaped logistic function which predicts two maximum values 0 or 1. So if it's a binary classification like heart disease yes or no, diabetes yes or no, Titanic survival prediction yes or no, you can use, that's a classification problem, right? In that case you can go with logistic regression, and it will give a S-shaped curve instead of a straight line, And there is also options. If you have multi-class, then what will happen? Instead of 0 or 1, if you have 0, 1 or 2, in that way there is also a method for it. I'll explain. So the formula for logistic regression is 1 by 1 plus e power minus x. Okay, so we are taking exponential here. So for example, if you are having a value x, so what will happen is that x value is now applied to this formula and the new value is plotted. So like that, if you plot, it is going to give you a sigmoid curve or S-shaped curve like this. So you will be having a threshold value which is 0.5. So now if you are giving a new data point, I'll be applying it to this formula, and if that point is greater than 0.5, then it is actually going to be given or predicted as 1 based on the threshold value, and if it is below this threshold value, then it will be predicted as 0. So that's how simply logistic regression works. In logistic regression, we use the concept of threshold value, which determines the probability either 0 or 1. So we will be having the 0.5 as threshold usually. And the type, when we talk about the types of logistic regression, we have binomial and multinomial. Binomial regression is two class, 0 or 1, yes or no kind of. So when you have multinomial, it can be 3 or more classes too. For example, like you are going to predict either a cat, dog or a sheep or a circle or a square or a rectangle. That will be a multinomial logistic regression. So in binary classification, you understand how it works. We are using the formula and it is giving a S-shaped curve based on the threshold value. The output will be given as 0 or 1. But now if you have another class which is going to be 0, 1 or 2, how will you have? You will be having another line. No. So how it will done is, I'll tell you, this is a sample of logistic regression, Titanic classification. So the answer is to find alive is yes or no, survived or not. And the formula, so it's a sigmoid curve formula. So before talking about how multi-class works, let us understand furthermore about our logistic regression. So if you talk about linear regression, we used a straight line, right? Can't we use the same straight line here to classify them? Like if this is beyond that, it is 0, or beyond this is 1. It's not possible. See here, when you have a data point like this, you cannot actually classify them with a straight line. It's not actually possible. Here your output is a continuous one, so we have given here your output is a continuous one, so we have plotted a straight line to find the relationship with our straight line formula. But here it is not at all possible because the output is categorical, 0, 1, etc. like that. So here what you are doing is, instead of that, we are going with this model, and it uses this formula actually. So 1 by 1 plus the exponential of the negative value of this value. This is once again going to be the straight line equation, b0 plus b1 of x. That is applied here, and this new value is plotted. So based on the threshold value, the output is predicted. The why now it makes sense. So there are two things that explain why linear regression is not suitable for classification. The first one is that linear regression deals with continuous value, whereas classification problem have discrete or categorical. And the second problem is regarding the shift in threshold value when new data points are added. So when you have a new data point, you cannot move here or there. So that's what your problem here. But when you go with a logistic regression, it actually works well in classification. And they uses the same formula of straight line. With that formula, it is applied to this new formula to get your sigmoid curve. So now going with the multi-class classification with logistic regression, binary is fine. How are you going to predict a multi-class classification? So what will happen is, it will be splitted into parts. See here you are having like F1, F2, F3 and your output. Okay, so these are features and this is your output. And your output is 3 class, O1, O2, O3. 3 classes are available. So what will happen is, it will be splitted into parts. Okay, first time it will be considered O2 and O3 together. O1 will be a different class and this two will be together a class like this. So now it will perform classification between these two based on the sigmoid curve. Like that it will take the new point. So like that, if you have 3 different class, then 3 categories will be separated. So if you have 4, then 4 will be splitted in that manner. So 3 will be here, 1 will be separate, then new 3 will be here, 1 will be separate. Like that they have been classified. and your final output will be like this. So it is going to make an output like this. If O1 is good, then you will be having a +1, the remaining things will be -1. So like that it is going to map the values. For example, it is like 1 versus all, okay, 1 versus the rest of all. In that manner the output will be predicted. So finally you will be getting a probability. So for O1, O2 and O3, if you make a new prediction, you will be getting a probability of how much O1 probably, how much O2 probably, and how to O3 probably. Based on these values, whoever having the higher probability, here O3 is having, and that will be your prediction output for this particular new data. So that's how our logistic regression works on multi-class and binary classification. And in this session we have seen about linear model. So in the next few sessions we will be seeing about further more algorithms. Thank you.